Okay, hello everyone. So I think we need to set a schedule for our final exam. Okay, since we also have another class right with mechanics. If mechanics June 6th, how about our course? Should be fit or maybe earlier, like next week? Do you think that's okay or? Next week, okay. Okay, so next week, so I will try to finish this last part by today and Thursday. We are still one more sections. This is the last part, which we are focused on polymer characterization. So far, what I prepared here, there will be a lot of some mathematics formula, but I don't want to like I don't want students like just memorize the formula, but I want you to a little bit understand the process and how we get the formula. All the notes I will try to provide after we finish. So last sections, I will try to upload by today the notes, so you can prepare for A4 for your final. Okay. And I hope you can prepare your notes very well. I'm trying to provide all the notes that is necessary. Okay. And if perhaps we need to have some additional content, I will provide maybe additional content if the content is related to this last part. So our last part, okay, that will be in the lecture will be the polymer characterizations. Okay. Okay, so characterizations. When we characterize our polymers, what should be prepared is how to prepare the samples, right? How to prepare the polymer itself. So we need to understand the polymer behavior, okay? Especially if you want to characterize, the most obvious way is to solve the polymer in some solution. So that is the first thing we need to take. So this content will be defined by at least this, I think 1, 2, 3 big groups. The first is like introductions, polymer in solution, and its thermodynamics. So you will see some thermodynamics formula, and I will explain a lot about that formula. And I hope you get the idea. And if not, then perhaps you can read more about the topics. Okay. And the second one is the process and how we characterize. So there will be 3 categories within here. The first one is the osmometry, light scattering, and the gel formation chromatography. For today, if we are taking a good time for learning, my plan is maybe up until this light scattering, and then the rest, these 2, will be on Thursday, and that's it for our course. And next week will be final exam. Next Monday. And I think that schedule will be, I think, very, very good if you have other schedule, like the other course, the mechanics material. It's supposed to be in 6, so I think you can have more flexibility within the schedule. Okay? And I hope you can also prepare your A4 notes within this week. Okay, now let's start from the first one. Okay, so we need to understand the polymer in solution and thermodynamics of mixing. So polymer in solution. Okay, so there are 2 things that I would like to describe within this topic. So we are going to see how we can see the polymer itself, the formations in solution, and how we model the polymer. And then, aside from the structure, we can also see how we could also understand polymer through the thermodynamics, okay, or free energy jigs. Okay. Especially if we want to mix the polymer with solvent or polymer with other polymers, okay, we're going to see these two things. Okay, perhaps let me just get you the details. Okay, so if we are just taking the polymers, like for example, just like this random linear chain like that. Okay, suppose that this is linear. Okay, but the real truth that is the polymer might be like the noodles, right? So it will be coiled randomly like that. Okay. And how to analyze the polymer. Okay. If this is just a single chain like this, perhaps it's easy if we could, for example, we know the monomer and we know the perhaps the dimension, we could measure easily. But if we are having like coiled like this, and this is the real structure that we might have in polymer, how we analyze? One way to analyze is if we take the end of the polymer with another end. Let's say the end is here. Okay? So we have some certain distance that some way or somehow usually described by the r. So this is this end-to-end distance. Okay, and this will be, I think, frequently I will discuss this distance, okay, between these two chain ends. Okay. Okay. So the simplest way to measure the dimensions is by taking the what we call the contour length, which is this L. Okay. So contour length. So that is multiplication by the n. N is the number of monomers. So let me write here how many the monomers inside, and then the small l here is the length of monomer. So of course, if we know how many monomer inside and we know the length of monomer, we could simply model the contour length. Okay, and of course, the numbers and the monomer's length will be obtained by some approximations. Okay, that later we could see how it ends. And for molecular coil, because we simply cannot see how the length in between, right? Because this coil is really random. So we could see one parameter, which is we call R. Okay? R is the distance between two chain ends, or we say the distance that's separating the chain. Okay? And then we could also take the distribution rate or the probability of the distribution of R that is usually represented by the root mean square, okay, end-to-end distance. Okay? Or we say R squared with power of half. And this is the average probability. And somehow we could also see, actually, we could see the polymers, okay, how we model the polymers using vectors. Okay? If you are taking the 3 axis, we can take the vectors, and somehow we could also model the vectors and then find the magnitude value, which is usually take the square, right? And then take the square root. Okay. So it's similar to that, okay, to give you some idea on this probability. Okay. And aside from the R, we could also take the S, okay, S squared. I think S will be in the different section, but I will write here first. That is for the radius of gyration. Gyration. This is if chain is not linear. And then there are some mathematical value on how this r squared will relate. Basically, we are going to use some vector, but I think I will just skip that because that is just for introductions. Okay. Now, this is the simplest model. Okay, as I mentioned, we are going to describe the polymer with a vectors. So let's say we describe R as a vector that is separating the two ends, okay? And we simply write the relations that we call P and W. So this is the model for free jointed chain of N. So there will be many monomers with length L. Okay? And there will be no restrictions upon the angle. Okay? Angle means how this, because remember, I think if you learn the stereochemistry or plasticity in polymers, the polymers can be cis, trans, right? And then perhaps the best way to visualize is the polymers tend to have, like for example, this part here, it can rotate, right? You can have some rotations. You can have some modes, can rotate through here, through that angle. Okay, so this is not having any restriction. So it's free. Okay, so it's free. So we take that, and then we simply write, this is what we call the probability. Okay, just to mention, there is some notes on mathematics here, but let me just explain in a quick, easy way. So this will be this B is supposed to be not B, it's supposed to be beta. Okay, I forgot to change this. So this is beta, this is beta. Yeah, I don't know, in textbooks sometimes they write the symbols not in a perfect way. So this is going to be polymer, or not polymer, probability at N at a point XYZ, or at point W, which is XYZ. Okay. And we can also take the XYZ into our R. Okay, we take x squared plus y squared plus z squared is equal to r squared. We could also remodel the formulations and make it into r. Okay, r squared. Okay, this is beta. Beta is supposed to be a constant. Okay? A constant. And this can be also write as WR. Okay. And then we can plot this probability density function. Okay. So this is probability density function. So it will describe how dense the polymer can be. So describe, let me write here. Describe how dense the polymer is. Okay, the R, we can also write R as a radial function because it's supposed to be remodeled after the polar. Okay, so this is plot with these two probability density functions. Okay, so A is for the XYZ and B is for the R. Okay, and you will see that we have if you know the distribution functions, one of the famous one is we call, usually using the normal distribution, we call the Gaussian function. And this is the Gaussian modes. Or Gaussian distribution. Gaussian distribution. Okay. Of course, if we look at these two, the radial distribution, it has symmetry, right? It has symmetry because the radial will be, we can compute all the necessary point like a circular, but here we can, this is more direct from end to end points, from one point to another point, from xyz to another xyz. Okay. So just a little bit conclusion here, that is in Polymer's solution. So in Polymer, if we put in the solution, first is we get random coil geometry, and second is the distance will be much smaller than the total chain. Okay? So the total chain, with if we take the random like that, okay, the end point here is usually smaller than the extended chain, and you can take that as assumption as for now. But when we try to model for more experimental, for more some other modelings, we could see that this is going to be true. So this will be true that this arc will be very small if you compare to the whole chain of the system. Okay. And if we increase the restriction, so for example, if assumption for the previous one is we don't have any bond angle restriction, so if we take the bond angle restriction, the coil in geometry will be also increased. So the randomness will be increasing. So that's just a quick note. Okay. Okay, that's just for introduction to polymer in solution. The next one that is probably take times to explain is if we compare the solution itself, how we mix polymer in solution in perspective of thermodynamics. Okay. Some of terms I believe you have learned before, but I think it takes time to explain. So let me explain, and I hope we can understand from the thermodynamics. Okay. So thermodynamics of mixing. So one of the things that I mentioned before is that when you mix polymers, the polymers that doesn't mix very well. Okay, and we are going to see why. Okay. Okay. Firstly, that is if we could take some formula. Okay, if we try to mix between one material and the second material, let's say G1 and 2, we could have this mix frigid energy, subtract with the summation of both energy of material 1 and material 2. And we could simply take this into our basic formula for Gibbs free energy, that is the enthalpy, total change in enthalpy, minus T delta S, which is the entropy. Okay. Now this will be very important if you are maybe not remembering your basic physics or chemistry. So let me explain it in a more convenient way. So the enthalpy, delta is enthalpy, delta S is entropy. So enthalpy, okay, this will relate to the interaction in between segments. Okay. So we are going to set some terms which we call interaction. Okay. So if you take one atom, how many atoms it will interact? So one atom and another atom, how can they interact with each other? It will relatively relate with that. Okay, so enthalpy relate with the interaction. But entropy is how we see the disorder. Okay? So we say it is disorder measurement or the more chaos, the more high entropy is. Okay? Or in our way to see, if we look more into micromolecules or in a really small world, this is how it can be, how many paths it can move. Okay, so if you think like a small molecules, like maybe if you think like a solids, okay. Let me just explain in a quick. So if you think like solid, okay, and then you have more space in between. So if you compare these two, let's say this is A and B. Okay. A, the particle, it seems that they don't have much spaces, right, to move. But here you have like free spaces. So you can see that it can move like that, right? In terms of entropy, this is have higher entropy, that it can have many paths. Or in our words in chemistry, we say states. Okay? That it has many states. And in our terms here, because we learn in a small world, in the micro world, we say it's microstates. So it has more flexibility to move, okay? To find a way that is much more safe and less energy, right? So like, for example, why like metals, okay? I'm trying to give you some analogy, like metals. Metals in nature, they are corroded, right? They are in their like if you are exposing any metals, if you don't maybe do some treatment, you will get rusty, right? You will get different color red, because the corroded one is the one that is much more stable. They want to make their states more stable, so they prefer to go to the corroded one. Okay, so this is also the same. So they want to go to the place where they are much more stable, and they are probably like you prefer maybe between sometimes in the morning if you have like morning classes, between go to the class or okay, let's just take 5 more minutes in bed. You take 5 more minutes, right? Because you feel so happy, so convenient, right? So this is similar. Okay? So this convenient way to find our states. Okay. So that's just a quick introductions for the thermodynamics. And then we could describe this in more convenient way for the entropy is with this formulation. So S, then K, and then we can have this omega. So this is what we call, the K is Boltzmann constant, as we mentioned here. And omega, what is omega? Omega is the microstate that we mentioned. Okay. And then if we apply in the ideal solution, then we could have a combination for both material 1 and material 2, that it has microstate for both 1 and 2, and then minus how it will be from material 1 and material 2. Okay, this is simply related to what we have in the previous one when we take the Gibbs energy 1, 2 minus G1 and G2. Okay. So if you look here, this is the explanation. So the omega 1, omega 2, omega 1, 2, they are total numbers. Let me just give you some underline. So this is total numbers of distinguishable spatial arrangement of the molecules in the pure solvent, the pure solute, and the ideal mixture. Okay. So ideal mixture is the 1, 2. And let's say 1 and 2, 1 is the solvent and 1 is the solute. Okay. And else? Okay, and then since we conclude that the number is 1 for both pure solvent and pure solid, we assume it's 1 because they are in 100% the material. So we could also just take this account here as this 1, which is 0. So we could take the combination, assuming that this will be just related to Boltzmann and the microspace. Okay. Okay, and next is let me explain a little bit. Okay, to give you more idea. I think I need to just go through like that, and then copy this and make it into here. Okay. Okay, as I mentioned, the microstate it will describe by the spatial arrangement. Okay, as we can see, the first case, it has more free spaces right there, right? But the second one is maybe small like that. So it's changing its position, but not much. So we can say that this has more ways. Ways means the microstate. And the movement, how we move or how the particle moves, this will relate to the vibrational degree of freedom, which I think I don't have time to explain more about this, but this is what we call. So every particle, they are vibrating. So all particles, like in your body, in everything, living things, inanimate object, they are having their own frequencies. Okay? And well, it's related to physics and the string theory, but I think I'm just skip that. So, okay, so it's just particle movement, vibrational degree of freedom. So let me. So what we are having here is the conclusions, is to make this order becomes ordered. The transition can only be driven by entropy. Okay. Okay, I think I need more space again, but I think start from here. Okay, let me write again that this S is K ln. Okay, let me remind again. So next week we will have a final exam. Okay. Okay. Now let me have one more space here to get you to another explanations. So another note that is I think important is from the enthalpy side. Okay. So if we take this, so this delta S, this will generally is positive. Generally will be positive. We are going to see also later, so with some formulations in mathematics. So this will be so more different position or states can be obtained or can be reached with mixing two components. So whether it's going to be high or low, the terms for the delta S will be having a positive terms usually for mixing. And so now, what's happened about the enthalpy? Now we can describe this. But the delta H or the enthalpy, okay, this will depends on interactions between polymer chains and solvent. Okay. If the interaction between solvent and polymer favorable, or they are likely to be interact, then chain will be surrounded by solvent. Which we call the terms here will be swelling. Okay. Swelling is when the real polymer is larger than the ideal configuration. And to take this swelling, to make it happen, the swelling has a factor we call alpha. So if alpha is greater than 1, which means it will be swelled. So this will be swelling factor. Okay, that's the first case. The second case, if interaction polymer and polymer, so between polymer is favorable, so they like to interact between polymers, not with the solvent, then chains will be surrounded by themselves. We say that this is going to be collapse or precipitation. This is when the alpha is less than 1. I think I can make this a little bit to the left side and make it a little bit smaller. Okay. And then when alpha is equal 1, which means there are some polymer that attract to other polymer and some polymer attract to the solvent. That is what we call theta conditions. Okay. Let me write here. So because if you are later do some experiment and somehow you will study about polymer, you will likely to read some parts of your books or maybe some guidance when you use some equipments. There will be some mentioning about theta conditions. Okay. And usually we are going to use some modelings to help with the procedure. So if interactions are exactly the same between solvent and polymer, so all forces acting on the change will cancel each other. So this is we call pseudo ideal. So pseudo ideal or theta. Theta like an angle theta condition. This is when alpha is equal 1. So if we are going to illustrate how this might happen, so suppose that we have the polymer. If the polymer are attracted with the solvent, and it will be swelled, so it means that the solvents, it can enter the space in between the polymers like this. So suppose that this is the solvent, the blue one is the solvent. And at the end of the day, your polymer will be swelled. Okay, so the solvent will be going inside, like it can absorb and then it will be swelled. But if the polymer attract with other polymer, with other segment of the polymer, then it means that this polymer will be coiled by themselves and the solvent is not going to enter. Okay, so it goes like that. So this is swell, so this is swelling, this is collapse. Okay. And the last one, this will be some of them collapse and some of them swell. So it's like in between of these two. Okay. So perhaps some of them like coiled like that, but some of them having a solvent. So perhaps solvent is here, but not in between of the coiled one. Okay, perhaps. Okay. This is just my illustration. So this is theta. Okay, that's a little bit interaction on enthalpy and how it relates to the swelling factor and how it goes at the as the illustration. Now let's went back to the entropy. Okay, let's went back to entropy. So this slides. So let's go back a little bit on entropy. Okay, and before I'm explaining on the right side what this is, okay, let me just give you some models to help you understand what we are going to do. Okay. So suppose that we have three by three row and column. Okay. Okay. So let's say we are taking so let's say we have some particle. And the easy way to model the particle is through lattice model. Okay, so this is a lattice model. Later we are going to see the polymer will be also assuming in this lattice model. Of course, lattice seems simplified, but we can see some model through this method. Okay, so this is going to be N1. Oh, sorry. This is N1. This is N2. Okay, so we have two materials. And then suppose that the microstate for each of them are 1. Okay, so if we are going to mix the two, so suppose that we take another one. Okay. Now, how many ways we are going to combine these two? Okay. How many ways we are going to combine this? Okay, let's say we take one blue here, green here, okay? Or if we take the one here, okay, let's say that is the first one. So this will be N1 plus N2. Okay. And then we take, or maybe let me write here. So the microstate for 1, 2 is, first is we take both N1 and N2, like this one. Okay. So they occupy two space, right? Two space there. So we take N1 plus N2. So the probability on how this microstate has come true is, then the next part is we are going to take N1 plus N2 minus 1. Okay, because let's say we start from 1. Okay, so we already have empty space. It can be N1, it can be N2. And then we put 2, and we can write minus 2, and so on and so forth. This will be a factorial. Okay. So I'm going to write again. Okay. And divide the total, which is the factorial. Like I think in mathematics you learn a little bit on combination permutations, right? So this will be multiplication of the N1 factorial and N2 factorial, which correlates with this part here, which we can take the conclusions that this will be using factorial like that. And simply we can put this microstate inside the delta S. Okay, so that's how we get this formula on the right. Okay. So that's why you get this. And then what's next? Of course, this is not something that is practical in measuring something, right? In experiment, it's not practical. So we need also to simplify this, what this is about. And the way we do it, let me just skip some process. And we call the approximation is Stirling approximations. So I will write in the new page, that is this Stirling approximation. Okay? And remember the notes I will share later. Okay? After finishing the chapter, I will share later. And perhaps we need one more lecture on Thursday, just to make sure that we review all the subject. Okay? So the method we call the Stirling approximation. This has some little bit mathematics. So the Stirling approximation is this. Okay. So for large N, the number of molecules, the ln factorial will be approximate with n N minus N. Okay. And somehow we can also write something like this. Or if you want to write in mathematical models, later I will show you a little bit. Okay? Okay, we are going to have a break for a while. Okay. Okay, let's continue a little bit. So if you like to R, we could also take. So take R is K multiply with the, I forgot the numbers, okay? And then we could simply write in fractions that this is going to be negative R, change from K, okay? And then N1, and the fractions, and the second material fractions, okay? Okay, and then if you want to make it more simplified, we could also divide all segments by N0, which is this is going to be the number of molecules. So we could divide all segments by taking the N0. Okay. So we are going to have, this is equally to be x1, this is x2. Or if we take assumptions, so assume that material 1 and 2 equally in volume, then we could have the pi 1, which is the volume fractions. This is going to be V1 V total, and also we have the volume 2, the volume fraction 2 also as well. So this is volume fraction, and we could rewrite the formula. I'm going to write here below. So delta S divided by the number of molecules. This will equal negative R so we can write also like that. And since the volume fractions, if the total volume is 1, then this will be a fraction 0 point something, right? So ln with some 0 will be negative, right? So negative, negative, and negative. So it's always positive. That's why it's always positive. Okay. So no matter how you interact with your, how you make the path, the microstates, how many microstates you might have, the total for the delta S simply just positive value. Okay. So let me write here. So since this is going to be less 0, this is less 0, and this we have negative here. So we can simply write that delta S will always be positive from this point of view. So we could say that for mixing process, so entropy will always in favor in mixing. Okay, this will be very important. Okay, of course, in the exam, I would not question about the derivation of the formula, but I would like to ask some understanding from the concept. Okay? Okay. So this is if we have some materials with other materials, and we haven't yet focused on polymers. So we say that this is perhaps for small molecule transformations. But using the same assumptions with polymers, we are going to write something different. So let's write for polymers. What's the problem? Is the polymers will be larger than small molecules, of course. So we will have some differences in the formula, and then we cannot fit within the lattice like usual. But we are going to use chain of monomers. So how we are going to do that is basically, this is lattice molecule, what I mean. Okay. But we still use the lattice, but for monomers. For example, we are taking the molecules like this, and perhaps we divide this into a lattice. Okay. And perhaps this is going to have here, going there. Okay. And we try to model this monomer. Okay. So suppose we take similar concept as before. Let me write here. I still have the page. Okay, we still have. So let's say the first material here is the solvent. Okay, let me write the solvent. And the second one here is the, let me just write first. Let's say that is the polymer, and so we connect this and make it into, like, each of the circle is a monomer. And it can be in many ways, but I will just describe like that. It can be in random positions. So this is going to be solvent. And this will be the polymer. So what's the difference? The difference is we are going to multiply this n for polymer with x. So x will be the number of monomers in chain. And the assumptions, if the microstates for the material 1 is just 1, then the microstates for the polymers, this will be greater than 1, which means that it will affect the, so if we take the delta S, Sk, Ln 1, 2 minus Ln 1 minus Ln 2. So if this is going to be increased, and this is going to be decreased because of this combination between 1 and 2, then the delta S also going to be decreased. So you can imagine this is going to be 0 for the omega 1 equal 1, and omega 2 will be greater than 1. So this will resulting the delta S that is going to be decreased. So by this assumption itself, we could see that the omega for the polymers will be much smaller than the small molecules. Which contribute that it will reduce the delta S. So the explanation is that if we combine these two, so N1 plus Xn2, we will have less microstates. And this is simply the same conclusion as that. So less microstate because we multiply with this X, and then the way they can move will be limited. Okay, that's precisely if we try to draw. Okay, if we see the drawings, that this is going to be not easy to move, right? So we need to have another assumptions for this one. And let me skip some notes and process. Okay, so you can see here that at the end we want to define this. Okay, so we want to define. Okay, and this is how, for example, this is the chain of polymer. Okay, and it was surrounded by the material one or the solvent. Okay. Of course, it will also limited, right? The polymer itself has limitations for the states for microscale. But still, okay, we want to make it into the models. We have a problem here. But the way we solve this is by taking the x. Okay, by taking the x, let me write in here. So quick summary for now from the previous page, that polymers will occupy more volume, okay, because it's large molecule. And then we need to consider the difference in expression for volume fraction. So let me write first the expression before we go into the conclusions. So this is the expressions. This expression exactly like the previous formula, but we change all the N2 with x N2. So we add that. So all N2 will be added with this x multipliers. So taking the fractions and simplify and change all the N2 with x N2. And also change the K with R and taking the Avogadro number. Now we can have this formulation. So from here we get the formulations in which the formula is taken from here. So the volume fractions, all the N2 will be multiplied with sub x, which is the monomers number, how many monomers in the solution. So we are going to relate closely the chain with its with the repeat units. Okay. So we have this, and this is we call the, and we can also write right here. We can divide by the same similar what we have before with N0, and we can write pretty similar. And divide by x. So this is the solvent. And this is the polymer. And if you see, because of this x is large, it's large molecule, so x is bigger, so this part will approximate 0. and this part is still negative, because this is the same as before. So the only way the system can be mixed is through the solvent. Okay? So if you have two polymers you want to mix, the likelihood to be happen is nearly not possible if we take this model. So the solvent will trigger the mixing. Okay? So this will be, so since it's negative, okay, because of the volume fractions, it will promote mixing. And polymer, since the X is big, large molecule, so it will approximate, so it will approximate 0. So the polymer has a small contributions, not really triggering the mixing. Okay, so this is what we call, I think I forgot to rename this. This is the Florey-Huggins for polymer solvent. Later we are going to see also Florey-Huggins. We have some special parameter that will define this mixing process. Okay. So imagine if you take polymer system. So if you take polymer, for example, so this is polymer solvent. So for polymer, if we write here, let me write small pieces, negative R. Let's say this is divided by X. Both will be equaling to 0, and the result will be 0. So this is going to be mixed much worse for polymer. So from here, in quick summary, let me write in the top here. So delta S for small molecules, this will be bigger than the delta S for the small molecules polymer. And it's also bigger than the delta S for polymer. Okay. Now, in terms of the, oh yeah, this is supposed to be this one here, but yeah, let me just skip this. This is what I write here. Okay. So yeah, I forgot I prepared this. So let's just skip that. Okay, so next one is the enthalpy of mixing. So enthalpy of mixing, or the delta HM. Okay. Within this explanation, I will write the delta HM as the delta G. Okay, so the delta G, if we see from the particles, we are going to see that delta G12 is G12, and then it refers to each one of them. So if we take small particle, let's say we have small particle like that, and this is another one, and how we can break these two apart and how they are interact and making between these two and make this mix. This is what we call, this is G12 G12, this is G, let's say 11, this is G22. Okay. So the total contact will be this, okay, and P12 is total is the contact, the probability of contact, okay, probability. Okay. So the idea is we are going to see changes for a pair of molecules when we mix, how we can mix up these two particles, and then we can later to add all the possible contacts, okay, all possible contacts. We get this, okay? So this is the probability. So we get this Z minus 2 from our approach to the lattice in polymer. So let's say we are going to have P12 from lattice and taking the X segment per polymer. So let's say we have that. And we divide this by the lattice. So if we take one by one these molecules as its monomer, the two adjacent already occupied. So that's why we have probability minus 2. Okay? So this will be reflecting the number of sites that can be occupied. Okay. X is the segment, okay. And the phi 1, this is going to be our mean field, or the best way to illustrate this is sites that are occupied according to number ratio 1. Okay, but I will not describe further. Okay. And then from here, we are going to describe in more practical. So we are going to describe in a more practical way that we mentioned that the lattice parameter Z, the possibility the monomers have occupied, and the free energy is not really practical or not accessible. So we define another parameter, what we call the Flory-Huggins polymer solvent, which is described as this chi letter. This chi is equal to this, that minus 2 delta G12 over KT. Okay. Okay, and then we simplify all formula here, and this is also our assumptions as before. Okay, this is before we say that this is going to be equal in volume for 1 and 2, and we can describe within this delta G contact, okay, or this is actually the delta H, the enthalpy. Okay. Is also equal to delta HM. Okay. So by definition, delta HM is the free energy for the contact, the interactions. Okay. Yeah, I prefer using the H because sometimes you get mixed up this G contact with the E, original G. Okay, and then we are going to use this two approach, okay, for the chi and the delta H, and using the thermodynamics notes from previous sections. So we could take this as, so this is delta H. Let me remind you, this is delta H. Okay. This is delta H, right? To help you to write that this is actual delta H. So we can write from the previous one, we substitute all the components, all the equations. So let me just skip the mathematics and focus on here. So we can write that this is going to be equal to, at the end of the day, we get that total, it will be N1 ln pi, the fractions, and N2 ln phi 2, and then N1 phi 2, and then the fluorine Huygens parameter. So simply just substitute from the previous one, and then we have this. And this will contribute to this. So this one from the entropy, this one from the enthalpy. Okay. And if you want, we can also write in terms of the number of molecules, so we can divide with N0. So that all having the same parameter phi. And it's much more, I think, they are more similar in the writings. So this will be the entropy, the delta S. This will be the delta H. So you could describe, and as we mentioned earlier, that the delta S will mostly triggers the mixing, okay? Because they are going to be make things positive, right? Make things positive. So why positive becomes really important? Okay. So in thermodynamics, remember how to make this. So if you have a reaction, you have the delta G. What's different if this is positive or negative? What's happening if you have reactions? Your delta G is positive. Yeah, it's not spontaneous. So you want to make this delta G as negative as possible so that your reaction is spontaneous. Okay? So we want to make this delta G so that this is, we say, spontaneous reaction. So how to make it negative? So if we increase this, so if this is positive, it means that this is going to be more negative, right? More negative. So if we take this, and if we make this as small as possible, then we could make this all things negative. Okay? Hope you get the point. So this is going to be positive there. But the takeaway from all the summary that I've given is the polymers mix worse than monomers. Because first, if you take polymers, then it will decrease your delta S, which is not good, right? And then also the delta H also uh, will not trigger the reaction, especially if you are having polymer-polymer solution. So you want to take an ideal situation where you have a polymer and then you have a solvent, and you want to find a solvent that can have an ideal condition, which is a theta conditions that is going to have some of them are swelled and some of them are attracting the polymers. If you are taking the solvent that makes the swelling factor increase, it means that it's going to be swelling and it's not easy to measure. And the same way when you have the polymer-polymer attractions, which is collapsing the polymers, also not good for measurements. Here you want to make it in between so that we can take some measurement. So that's we in the system thermodynamically prepare the samples. Okay? At least the states and the equations we have learned, okay, from these introductions. Okay, the next part we are going to go one by one, and mostly we are going to focus on the molecular weight. The molecular weight. So the molecular weight we can find first through what we call the osmometry. Or here, before we go there are some explanation here that is going to be introduction to the osmometry. Okay. So in definitions, we have a parameter called the chemical potential. So chemical potential will be important for solvent and polymer. Okay. So we are going to describe. So this is the chemical potential for polymer, and this is for solvent. Okay. And the definition is this is partial derivative with respect to N1 of the Gibbs energy. So we use the same equation as before, and then we describe in the partial derivative. So we have this partial here. I hope you still remember the calculus. So a little bit calculus here. So first we take the derivative. So this would become phi 1, and then we get partial inside here, and then the second one here described as the up here we describe as the phi 2 chi, and then this one is another symbols. Okay. And then this is the for both volume fractions, and this is the relation. So we could take that, and also we can see from here some parts of it. That's simply that if we take the volume fraction, if the total of the volume fraction is 1, then you can say phi 1 is 1 minus phi 2, or you could say phi 2 is 1 minus phi 1. Okay. And then we could take that and make some, you can see, I think I don't have time to explain all this thing, but eventually, at the end of the day, we could define that using the partial derivative, we could have the idea that the chemical potential will be equal to this. Okay. Okay. And then taking, I think for other section, you will see for approximation they are using the series expansion from the Taylor-Maclaurin series. But I think I will just skip that. But to get this, okay. Now this chemical potential will be important to the osmometry. Okay, let me go through. Okay, so this is for solvent and polymer. So if we have a polymer, so we could do the same thing. Okay, we could do the same thing with some similar partial derivatives method. And what's the difference is we're going to see. So let's see the difference here. We have this. The previous one we have this. Okay. And now we have this x here. This x is related to the component that is supposed to be defining the polymers as a large molecule. Okay? That is, I think, in the previous section, we assume that X is the segments that is that is in the polymers, that contains how many monomers that is inside the polymer. Okay. So we have this for the polymer system. Okay. And then if you want to dilute the polymer solutions, this is what we can do. Again, this is the series expansion using the Taylor-Maclaurin series. This is just for your information. I will not ask this because this is in calculus. So calculus has a practical usage, right? Okay, so this is for ideal, okay, and we can have x2 as this. Again, we take this x, okay, this to symbolize the large molecule. So we could take some approximation for volume fraction and just molecular fractions, and then we can write at the right side that we could have these potentials. Okay? So all the things for the Ln we can write, and then later we could see it will be in use for the osmometry. Okay. Okay. This is just an illustration how we can prepare the polymer solutions through some dilution, but I think you can see from yourself for all these formulations. Okay, let me go through the osmometry first, and if we need, we can back to this part. Okay, so the osmometry, this is the determination of molecular weight. So there are at least four important things. So you will use the polymer solution, and you will also use the pure solvent. So you will use in the one equipment, and their solutions will be separated by the membrane. Okay. The membrane, the idea, only solvent can pass the membrane. Okay. And then you will see that we have some pressure inside the chamber, and then we will see there will be some difference in height, and I will give you the picture in the new page. Okay. So the idea is we are going to see some osmosis. Do you know osmosis? The diffusions in the, I think you learn in elementary school or in junior high, right? Osmosis. Elementary, right? Yeah, elementary school. Usually, if you see in plants, you will see how it's absorbed, and then it has a pressure. You can Google osmosis, and you can learn the Mandarin words for it, and you will know. Oh, okay. But the idea is very simple. Okay, let me give you the idea. The idea is very simple. Okay, before the picture, where's the picture? Oh, here's the picture. Let me give you the picture first. Okay. So this is the polymer, and this is the solvent, and this is the membrane. So the idea is there will be some diffusion here that will change this height. Okay. So we can get the height, and then from the height we could write the formula for the pressure. Okay. So pressure here is usually write as pi, the osmotic pressure. This is H, and then this is the solvent density, and G is gravity, right? Gravity acceleration, and H the height from this part here. Okay, you can write first the picture. I should write the picture at the beginning. Forgot to put in the first place. So this is just a normal pressure, but to differentiate the osmotic pressure, usually some textbook usually write in terms of time. Okay. But if you want to write like a P, like a normal P, like rho GH, like usual in physics, that's the same thing. And the same thing. And we first start from here. Okay, we first start from here. This is the same idea from the chemical potential from the polymer solution before. Okay, and then simply this is the integrations from the P0 to some P. Okay, so we are going to integrate the M1, which is the solvent. Okay, so chemical potential of the solvent in the solutions. Okay, so M10 is the pure solvent. The chemical potential of the pure solvent. So idea is when the pressure is equal, then the diffusion will take place, and the osmosis will take place. Because the pure solvent is higher than the just a regular solvent. Okay, I think you can read the notes later on, but from here we are going to see some little bit calculus, partial derivative for both of this. Okay, so we could take this G, and then this is from before, and we could take the G into B, okay, and then make it into B1 here. That is in our definitions, okay, in this osmometry. And simply, okay, for all the definition here, the final result is this, okay, which is this is the different pressures, okay, and this is the volume. We say the flow volumetric, okay, the partial derivative of this V with respect to the molecular of material 1 or the solvent. Okay, and then from this part we could see some notations. Okay. And as we see from the previous part, that for dilute polymer solution, V1 is equal to the molar volume 1 of the solvent, and then we have this. This is very similar to what we have before. So we can simply write down that approximately this part will equal to this. So just x n2 over n1. And then we could take this and make it into this. Oh, this f is actually 5. Sorry. I haven't checked here. So this is supposed to be 5. Let me write here. Let me write with white first, and then okay. Okay. So within this approach, we could take this is from the solutions before, and then we could take that into our osmotic pressure equation. So taking the dilute polymer solutions equation, and then put this relations, and we get this. Okay. So this is actually from what we had before, and then substitute the Florey-Higgins expression. Okay. And then from this, we go here. So let me write. So first is this, and then go here, and go there, and go here. So N2 over V, we could also write in more meaningful way because we can relate to this coefficient. So this coefficient is really important because this is the one that we want to measure. So this is the one that we want to measure. So we want So our goal, measure the molecular weight, right? Which is within this, we can see that we could have this. So from this pressure, the osmotic pressure, somehow we can say we could have some constant, and we could set up some experiment, and then we could see that we can find this. Let me give you some specific ideas on how we could set up some experiments. Okay. So what we can do is, from this part, we still have this V1 actually that is still not really good for our approximation. So we want to remove this V1. Okay, so we could get this chain segment, which is the V2 over V1, this is actually related to the degree of polymerization, but let me just take this as a chain segment, and then we have the density of polymer, which is the ρ2, and we could exchange all the things here. So V1 ρ2 squared, and then we could make this V1 ρ2 squared, and then the half minus chi as this, and this should be chi and rho. Let me change first. I forgot to change. Actually, I have changed, but I don't know why it doesn't change. So this is chi. This is rho. Okay. So set up this and make it into this we call the virial equation. So this is actually up until here. Okay. So this is actually up until here. But it can be modeled if we have more. So we can have A3, A4, A5, and more. But the idea is the A2, this A2 is the slope. Okay, this is the slope for the linear equations. Okay. So if we take, for example, if we take some graphs, between the pi over C and then the C over G, or the concentration here, if we take at 0, so we could get this as our 1 over m. So we could take, so if we make a good approximation for the linear equation, we could find the molecular weight. Okay. So here, molecular weight can be determined through the intercept. Okay. And the slope is actually this A, or you could say that it's also related to the chi, the Flory-Huggins parameter. Okay. So if we can make this and make it make extrapolations, and then we can get the molecular weight and the Flory-Huggins parameter. So we can find, the idea is we can find the molecular weight and the Flory-Huggins parameters, which is the chi. So this is the slope, this is the intercept. Okay, I think I will finish until here. So Thursday we are going to finish some parts for this characterization, which is the light scattering, gel formation chromatography, and for other method as well, like functional groups. Okay. And hopefully it can be finished within 1 hour. Or if I have more discussion, I will give you some notes, okay, just for additional notes. So I think that's all for today.